Hey guys, welcome to your Chapter 10 Lesson 2 notes on simplifying radicals. You'll have a radical time. By the end of the day, you'll be able to simplify radicals involving products and quotients. Remember, product is the answer to a multiplication problem, and a quotient is the answer to a division problem. So here we go. When I talk about a radical, the radical symbol is always this guy. He's misnamed the square root guy because he's only a square root if he's got a 2 right there. By the way, if there is no 2, there's a 2. It's just hidden. Okay, it's an assumed 2. But it can be any number. We can put n there. Here n is called the index of the radical. And then we'll have some number inside, or some term, some expression in here. The guy under the radical symbol, we call the radicand. And by the end of the day, you're going to put the can in radicand because you can do this. Ha ha. Okay, anyway, this guy's called the radical. Sweet. Okay, cool. Now, your key idea of the day is we're going to simplify radical expressions. And how do you know that a radical expression is simplified? Well, there are 3 ways, three conditions that must be met. First of all, the radicand, which is the guy under the radical sign, he can't have any perfect square factors. So what we do is we factor them out. We factor the radicand. We make sure that there's no perfect squares in there. Secondly, you can't have a fraction as your radicand. And finally, you don't have the radicals, you don't have this guy in the denominator, also it's right there, of a fraction. So in order to combat that, we do a process called rationalizing the denominator. We're not going to rationalize it as in like justifying it and say, oh yeah, I did this and it was okay because it all worked out and yeah, I rationalized my... No, that's not what this is. We're going to make it rational. Fun fact, that's what my name means. It means rational. Anyway, so I like pictures. And let's draw 3 ways that this could go bad. So if you have a perfect square under the radical, like if you have x squared, then you factor that out, that's just x. Okay, so if you have a fraction, you can't have, a over b. We'll get to how to fix that. You also can't have, like some number a divided by the square root of b. That's going to be what rationalizing the denominator is all about. Okay, so here, these guys are simplified because they don't have any perfect squares under the radical. Awesome. They also don't have fractions in the radicand. There's a fraction underneath here, but that's okay. And also, they don't have any radicals in the denominator. So, good job. Okay, this first one is not simplified because we can break up 12. That's the square root of 4 times 3. So that's the square there. That is equal to the square root of 4 times the square root of 3, which is 3 times 2 rad 3, which is actually 6 times the square root of 3. So this guy is simplified. This guy is not simplified because he's got a fraction in here. So that breaks rule number 2. This breaks rule number 1. And you guessed it, this breaks rule number 3 because we've got the denominator has a radical in it. Yuck. Okay, we're going to, in order to simplify our fractions, I already used what's called the multiplication property of square roots. I used that right here when I said that, oh, you know what? I have the square root of 2 numbers multiplied together. That's the same thing as their square roots multiplied together. So that's super de-duper. Our example is right here. The square root of 12 is equal to the square root of 4 times 3, which is equal to the square root of 4 times the square root of 3. So we're going to say that's the example. Yay. Okay, here, let's use it in two places. First, let's simplify the square root of 72. 72 doesn't have a perfect square root, but we can get it there. When I see 72, my immediate thought is that 72 is 9 times 8, and that's a fine place to start. I could do 72 is 36 times 2, and that would actually make it faster. But I want to show you that you don't always have to take the fastest route. So I'm going to break this up as the square root of 9 times 8. Because check it out, 72 is 9 times 8, so I'm allowed to do that. But now I can use my multiplication property of square roots to say, oh, the square root of 9 times 8, that's the square root of 9 times the square root of 8. And guys, the square root of 9 is 3, so that's neat. But 8 is 4 times 2. So I can continue to break this up as the square root of 4 times the square root of 2. Square root of 4 is 2. Here. Ta-da! I'm going to start all over. Square root of 4 is 2. So we get the square root of 72 is 6 times the square root of 2. Isn't that super neato? We could have gone much faster by saying the square root of 72 is equal to the square root of 36 times 2, which is the square root of 36 times the square root of 2, and hey, look at it. Square root of 36 is 6. Haha! So, whatever's the faster way, you can do that. Now, sometimes you gotta really work with it. Oof, let's figure this guy out. Well, we're gonna keep the negative m the same, and then we're gonna break this guy, we're gonna break this guy up already, square root of 80 and the square root of m to the 9th power. Now we're gonna look for square roots, because we don't have any fractions, so that's really nice. So we got to figure out, okay, square root of 80. Now when I see 80, I think, oh, 80? That's 8 times 10. But neither of those is a square root, so that's not going to be very helpful. So instead, we're going to break up 80 as 16 times 5. And then m to the 9th, we're going to break up as m to the 8th power times m. So here we've got negative m times the square root of 16 times the square root of 5 times the square root of m to the 8th times the square root of m. Wow, that's a lot of square roots. But the reason I broke it up like this is because the square root of 16, 16 is a perfect square, so that's going to be real nice. And guess what? M to the 8th power is also a perfect square. Let me show you why over here. So we have m to the 8th power, right? Remember our our exponent rules is if you have a power, that's a product. So 8 is 4 times 2. And since we have 4 times 2, we can say that's m to the 4th squared. Oh, hey, look! So m to the 8th power is equal to something squared. Oh, isn't that super cool? So that means the square root of m to the 8th is just m to the 4th. Wow. And the square root of 16 is 4. Awesome. So that worked out real nice. What are we left with? Negative m times 4 times the square root of 5 times m to the 4th times the square root of m. Okay, well now I need more room. Weep. Weep. Took my highlighter with me. Okay, so now let's combine like terms. How many m's do I have? I've got 4 of them. Nope, 5 of them. So that's negative m to the 5th. How many normal numbers do I have? I just have the 4. Times 4 times the square root of 5 times the square root of m. We're one step away from simplifying this. First, I'm going to do just a little bit of rearranging that is. I'm going to switch the order of m to the 5th and 4. And then we can actually use our, what did we call it? Multiplication property of square roots backwards. And we're going to combine, hold on, I dropped my pencil. Okay. And we're going to combine these two guys back into one square root. They're going to move in together under this little house. Aww. So the square root of 5 times the square root of m is the square root of 5m. And now we are simplified. How do I know that we're simplified? Well, I go through my 3 conditions. Are there any perfect squares under the radicand? Nope. Or under the radical? Nope. Do we have any fractions? Nope. Is there in the denominator? Well, we don't have any fractions, so that's not going to do it. So that's multiplication, but what happens when we have fractions? Well, I'll tell you. We use the division property of square roots, which says that if you have the square root of a fraction, it works exactly as you would want it to. It's the fraction of their square roots. Oh, how precious is that? Oh. For example, if you have the square root of 100 divided by 25, that's equal to the square root of 100 divided by the square root of 25, which is 10 over 5, which is 2. Yes, Miss Van Dyke, but couldn't we have also said, oh, the square root of 100 over 25, that's the square root of 4, because 100 divided by 25 is 4, which is the square root of 2? Yes, you can also do that. Yeah. Okay. So here, we can take our radical and split them up. Since we're dividing since we have division in a radical, we can just divide the radicals. So we have the square root of 144 divided by the square root of 9, which is 12 over 3, which is 4. This is because 144 divided by 9 is 16. Aw. Oh, this one is not nearly as nice, but we can still simplify it. Okay, so we need to take this radical symbol, and we need to put him top and bottom on our fraction. Square root of 8x squared over the square root of 25. Well, the square root of 25 is cute. It's 5. Aw, so cute. Up top, we need to split this guy up. That's the square root of 8 times the square root of x squared. Square root of 8? Oh, let's just do that down here. Okay, so the square root of 8 is equal to the square root of 4 times 2, which is the square root of 4 times the square root of 2, which is 2 rad 2. So I'm just going to take this whole hot mess right here. Square root of 8 is 2 rad 2. And I'm just going to be like, okay, square root of 8, that is 2 rad 2, because I did the work down there. The square root of x squared, that's really nice. That's just x, but careful, because this looks like, oh, this is the square root of 2x, but it's not. It's the square root of 2 times x. So to avoid that confusion, we always put things that are not under the radical in front of the radical. So that's 2x times the square root of 2 all over 5. And now we are all set. So that worked out real nice because our denominators, here we go. Our denominators were always perfect squares. So they came out to real nice numbers. But if the radicand, or rather, if the denominator is not a perfect square, then you need to do a process called rationalizing. Just kidding. This is rationalizing. What we are going to do is we are going to multiply. There we go. We're going to remove the radical by multiplying the numerator and the denominator by the same radical expression. This process is called rationalizing the denominator. Now that's really abstract. What does that mean? Well, it says, oh, shooties magooties, I'm not allowed to have the square root under my fraction? Ugh, blech. So instead, we multiply top and bottom by the denominator. We're allowed to get away with this because the square root of 3 divided by the square root of 3, anything divided by itself is 1. And multiplying by 1 is no change. So we're allowed to multiply by 1, and it doesn't change anything about our expression. So what do we get? Well, let's multiply across. Up top, we get the square root of 2 times the square root of 3. And then we get the square root of 3 times the square root of 3 on bottom. Now we can use our multiplication rules to say, oh, that's the square root of 2 times 3. Oh, that's the square root of 3 times 3, which is rad 6 over rad 9. Well, rad 6 we can't simplify anymore, so it's just rad 6. Square root of 9 is 3. But check it out. All we did to get from, all we did to get from this denominator to this denominator is we removed the radical, and that's what you will do every time. That's how rationalizing works. You're making this a rational number. You're just removing the radical symbol. So isn't that cool? That's really cool. So we're going to do this over here. What is our first step? We're going to multiply top and bottom by exactly our denominator. Yay! So on top, we get 5 times the square root of 8. And on bottom, we get, oh, do I dare do the shortcut? I dare. Straight up 8. Because all this does is it removes the radicand. Because I'm going to show you why. Rad 8 times rad 8 equals rad 8 times 8, which is rad 64, which is 8. It will always work. It will always just abandon the radical symbol. So cool. Now, what is the square root of 8? Oh, do these just cancel out? No, because this says, I'm here, I matter. So let's quick simplify the square root of 8 down here real quick. Square root of 8 is equal to the square root of 4 times 2, which is equal to the square root of, ooh, that's not a square root at all. The square root of 4 times the square root of 2, which is 2 rad 2. So I'm going to replace this. We got 5 times something over 8, and that something is 2 rad 2. We are almost done. Now we can reduce. Now we can say, oh, this is divisible by 2, and this is divisible by 2. So our final answer is 5 times the square root of 2 all over 4, and that's it. We cannot reduce this 2 with this 4 because this radical symbol is blocking us. Oh, yeah. There you go. Okay, cool. So your key idea is right here. These are the 3 conditions you need to have a simplified radical. Remember that you can multiply square roots and back again. And you can also divide square roots and back again, so long as you have a wonderful time on your homework.